Hello ladies and gentlemen, I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to bring to you another one of my articles. This one is entitled The Amazing Truth About Crepuscular Rays. Crepuscular rays is a term that describes the phenomenon of divergent light rays in the Earth's atmosphere. The term is used to describe light beams and shadow boundaries in the atmosphere, which diverge as a matter of perspective. In other words, that all diverging light in the atmosphere can be explained by the observer simply viewing light beams or shadow boundaries getting smaller due to increasing distance. Perspective is what makes a road seem to narrow with distance, and that's what we see here. And this effect can sometimes affect our view of the sky. However, looking at a road on the ground is not quite the same as looking at the sky, because everything in the sky is at an altitude of about 30,000 feet or more, and thus far above our heads, which should make the narrowing road effect less pronounced. In addition, the Earth's atmosphere is curved, and thus clouds in the distance will be closer to the ground and thus closer to us than if the sky had been flat. And this should therefore decrease the effect. That's illustrated here. So we have two observers. This observer is observing the clouds in the sky, and this observer is observing this road, somewhat like what we see here. Now, the difference in the distance between the beginning of the road and the end of the road will determine the perspective difference, or by how much the road will seem to narrow with distance. And this is basically about path length. So the path length difference is much higher for two ends of a road than for the cloud. As you can see, there isn't much of a difference in the length of these two arrows. For the length of the path of the light that travels along these two different lines. So the top of the cloud, as seen by the observer, is not that much closer to the observer than the end of this cloud. It is a little the path length is a little shorter in this case, but the perspective difference, or the length in the path, the length of the path is not as different as it is for the road. So we should not get exactly the same diverging effect that we get with the road. We shouldn't get exactly the same with the cloud. It should be less. So that means that a lot of diverging effects that may be observed in the sky that may be attributed to perspective are in fact due to something else. And as you can see, this is a chemtrail in the sky, and you can see there is a bit of divergence. It does seem narrower in the distance, but by not a huge amount. And this is because the observer is on the ground. The observer has to look up. There's quite a distance between the ground and the top of the cloud here, and there is quite a distance, the straight line distance, to that point as well. So the difference in the two lengths is not that much. Now in this photograph, and this is usually explained in terms of crepuscular rays, what we see is divergent beams which emerge from holes in the clouds. And these light beams are usually referred to as crepuscular rays. But can perspective explain what we see here? So in order to understand what is going on in this image and many others, we need to understand some geometric optics principles. The most important concepts in geometric optics are the fact that light travels in straight lines and that a light source emits light outwards in all directions. We know this because we are able to see a light source, like a light bulb in a room, no matter where we stand in that room. And here we see a photograph of a room. We can see several light sources. They look like light bulbs. And we know that wherever we stand in the room, we will be able to see the light coming from these light bulbs. If we stand from the perspective of where the photograph was taken from, we'll see the light bulbs. If we were to stand on this side of the room, we'd see the light coming from the light bulbs. If we were to stand on this side as well, and if we were to stand behind the table, we'd also see the light coming from these light bulbs. So that shows us that these light bulbs are emitting light in all directions. And that is illustrated here. So we have a light source, and that light source will be emitting light in all directions. So the light rays originating at the light bulbs go out in every possible direction, forming a spherical shell continuously expanding outwards from the light source. Now these light rays diverge. In other words, they never meet or cross over each other ever again. Now, the sun is much larger than the earth, as the sun's diameter is 100 times that of the earth. The sun is very far away from the earth. Sources of light that are far from a lens or detector are usually said to be at infinity. Now, what we have illustrated here is the sun and the earth. The distance between the sun and the earth is of course not to scale, but what we have is a good comparison of sizes. So the sun is 100 times larger than the earth, so it's much larger. The sun is a light source. It emits light, and every point on the sun's surface will emit light in every possible direction. So we see that illustrated here. These light rays are being emitted from this point on the sun's surface, and the same is occurring at this point and at that point. But not all of these light rays reach the earth. Only light rays coming from this point at a certain angle will reach the earth. And only certain light rays coming from this point will reach the earth. And these light rays are the ones that are perpendicular to the surface of the sun and come from this point that's in line with the earth. And from this one, it's also certain light rays that pointing in a certain direction that will reach the earth. This light ray, for example, will never reach the earth. It goes out way at a totally different direction from what would get it to get to earth. So it will go below the earth. Now we therefore have light rays that reach the earth, and as you can see, these light rays actually converge because they meet or they come together and therefore converge towards the earth. So these are convergent light rays that come from the sun. But the angle of convergence is actually very small because the distance between the sun and the earth is extremely large. So the angle is only 0.5 degrees or close to zero. And this means that we can approximate light rays coming from the sun which reach the earth, say that they are approximately parallel to each other. Now the angle of convergence is the same as the angular width of the sun at the earth, or seen from earth, and that's given by this equation. That's the diameter divided by the distance between the earth and the sun. So the diameter is twice the radius, and this is in miles, and we get an angle in radians, which is 9.27 times 10 to the minus 3 radians. We can then convert that to degrees using the conversion factor of 180 degrees equals pi radians, and then we get an angle of 0.53 degrees, which, as I said before, it's very low, it's close to zero, so we can approximate light rays coming from the sun as being parallel to each other. Next, we consider what would happen if we had a light source that was much smaller than the Earth in the Earth's atmosphere. Would the rays reaching the surface of the Earth converge or diverge? So this would be a light source in the Earth's atmosphere. It's much smaller than the Earth. It's inside the Earth's atmosphere. And as we know, light rays would diverge away from the surface of the light source. So inside the Earth's atmosphere, we would be able to see vertical light rays moving, diverging as they approach the surface of the Earth. And light rays that would go upwards would diverge as well. Light rays would be upwards and somewhat in the direction of the observer would diverge as well. All light rays would diverge from this light source. And then if we place an obstacle in front of the two types of light rays, say if we place an obstacle in front of light rays that are parallel from each other, and thus like the light rays that come from the sun, then what we can expect is some of these to be interrupted and absorbed and some to carry on. And this would create a shadow boundary if it was possible to create shadow boundaries which are parallel to each other, and the shadow would not increase in size with distance. Now, if we have a light source, a small light source within the atmosphere, then we'd have diverging light rays. If we place an obstacle in front of these light rays, then the shadow boundaries would diverge. In other words, the shadow would become larger with distance away from the light source. And next we can actually place a boundary with holes in it in front of these types of light rays, the parallel light rays. This would be like a cloud with holes in it. Some of these light rays would be intercepted, would be stopped by it would have to be a very dark cloud. White clouds still allow light through them. So some of these rays would not be interrupted by these clouds, and so they would continue. They would remain parallel to each other, and therefore the light beams produced by these holes in the clouds, which light is able to just go through, would create light beams that are parallel to each other. But the same would not be the case with a light source in the atmosphere. Light going through holes in the clouds would simply continue to diverge because the light ray started out diverging from the light source in the first place. So we would get diverging light beams. Now, it is possible to get divergent light rays by passing light through a slit or a small hole, and in which case parallel light rays can be turned into divergent light rays once they pass through such a hole. This is caused by an effect called diffraction. Diffraction is the bending of light around very small holes or objects. However, for this to occur, the hole has to be of a size comparable to the length of light. The wavelength of light. Visible light has a wavelength of between 500 and 700 nanometers, which is between 0.00005 and 0.00007 millimeters, or in other words, and we have 5 zeros, 000, sorry, not 5, 40000002 and 0.00004 inches. So the effect becomes noticeable with holes of a size of about 0.25 millimeters or 0.001 inches, and this is 1/1000th of an inch. So they have to be very small, extremely small. And holes in clouds are definitely much larger than that. So diffraction effects cannot be responsible for the diverging light beams observed. Now, let us apply this understanding to some images. So here we have a photograph. We see light beams. These are vertical light beams. They come down through holes in the clouds. So it cannot be perspective or distance from the observer, or change in the distance from the observer, that can possibly explain the fact that these light beams are diverging. This indicates that the light source is within the atmosphere and just above these clouds. So we have a small light source within the atmosphere producing this effect. There is no getting around it. Now, here we also have divergent light rays, or at least it seems like a light rays. They actually are shadow effects. Now, these light rays seem to radiate from just behind the cloud and indicate that a small light source within the atmosphere is illuminating the cloud. The light source appears to be white. The pink light below the cloud indicates a secondary and pink-colored source that is illuminating the atmosphere from much further away. So this pink light here. The sun is too high above the horizon for all blue and green to be scattered out of sunlight and produce red illumination. So whenever the sun turns red at sunset, it may look red because all the blue and the green has been scattered out by the atmosphere, and then the sun can directly illuminate clouds with that red light. This is not what we are seeing here. We're actually seeing a pink atmosphere, and the sun is way above the horizon. If the position of the sun simulator indicates the sun's position, and usually well, we would expect the sun to be behind the sun simulator, so the sun would have to be very high up in the sky, and so the sun cannot be producing a red light illumination of the atmosphere. But in addition, this light is not actually red, it's actually pink, which is a mixture of red and blue. And since blue would be scattered first by the atmosphere, this cannot occur as a result of a light source of the sun having turned, well, the sun couldn't possibly have turned pink when it's close to the horizon, because first of all, blue light is always scattered out, and then green light is scattered out, and then eventually we get red. But the fact that we have pink means that the illumination is only red and blue, and thus green seems to have been scattered out rather than blue. And green cannot be scattered out before blue. Blue is scattered out first, and then as sunlight goes through and more of the atmosphere, because we're moving towards sunset, then eventually the green starts being scattered out. But here, in order to get pink light, we'd have to have the green scattered out, and the blue was not scattered out, and that's just not possible. So this means that the only way to produce pink light in the atmosphere is by the atmosphere being illuminated by a light source that is actually emitting this color of light, pink light. Now, the fact that we are seeing shadow boundaries at all is problematic in itself, as the atmosphere is supposed to be transparent, and it is only if the atmosphere becomes opaque that such a phenomenon is possible. And this is the reason why during the day we may have shadows on the ground produced by clouds, but there is no such thing as shadow boundaries between the cloud and the ground. These do not occur. It's not natural because the atmosphere is transparent. Only an opaque atmosphere can produce these shadow boundaries that we see here. So this means that the atmosphere at this altitude has become opaque. Now, this is another very interesting, and here we see divergent shadow boundaries. Now, some of the divergence, at least, could be explained as a result of perspective, but as I mentioned right at the beginning, looking straight up and looking at clouds over there, there isn't that much of a difference, and the divergence that we are seeing here seems excessive, and most likely therefore due to a light source that is close to the Earth's atmosphere, and therefore emitting light that is diverging from that light source, and is noticeable because the light source is close. And if we were to follow these lines, we would see that they would converge at somewhere below the horizon or just outside the Earth's atmosphere, possibly where this light source is. But something else tells us that this is not produced by the sun. Because if the sun's light is now red because the sun is below the horizon, cloud shadows would be redder, not blue. Clouds are supposed to look red when illuminated by red sunlight at sunset. The fact that there is blue in the sky shows that the sun's light illuminating the sky is still full spectrum. In other words, the green has not been removed yet. It's still blue, so the sun should still be yellow, not orange or red. Now, the fact that there is blue in the sky shows therefore that the sun's light is still full spectrum. And this indicates that the atmosphere is still being illuminated by an orange light emitting source as well as by the sun. So there have to be two light sources in order to get patches in the sky that are being illuminated by two different colors. So what is actually occurring here is that the clouds are intercepting the orange light emitted by the second light source that's emitting this orange light. And that then leaves the sun's illumination to be seen. And that illumination is as a result of blue scattered light. And this is why the sky is usually blue. So whenever this object's illumination, which seems to be brighter than the sun, and therefore this object is most likely much closer to the Earth than the sun is, so it's brighter than the sun, and it would illuminate the whole sky if there were not clouds that were blocking this light. And where the clouds are blocking this light, we get shadows forming. And in the shadows, we actually see what's behind that light. And it's just not as bright. It's the sun's own illumination of the atmosphere, which in this case is blue. So we need the sun and another light source. And that light source is, as you can see, brighter, and therefore most likely much closer to the Earth. Now, so this is explained here again. I've explained it in other articles before, but as I have explained before, the sun's light can be divided into three colors: red, green, and blue. And these are the primary colors of light. This is addition of light, not paint. And so we have the primary colors: red, blue, and green. When you combine green and blue, we get cyan. When we combine green and red, we get yellow. When you combine red and blue, we get magenta or pink. When we combine all three, we get white light. Now, so the atmosphere scatters blue light, which makes the sky blue. The rest of the sunlight seems to come directly from the sun's position. White light minus the blue color frequency. So if we have white and we remove the blue, we get this. We get the green and the red without the blue, which means yellow. So this is why the real sun will look yellow from inside the Earth's atmosphere. And this is illustrated here again. The sun emits white light, so it will look white from outside the Earth's atmosphere. Inside the Earth's atmosphere, the atmosphere scatters or removes from the light that's coming directly from the sun the blue frequency or the blue color of light. And what remains to follow in straight lines and to seem to come from the sun's position is the green and the red, which combined gives you yellow. Now, closer to sunset, green light is also scattered out. So if green light is scattered out, we're left with just the blue. The blue and the green gives us cyan, which means that the sky will seem to be not so much blue, but cyan. So you will have a slight greenish tinge. It actually look more like what we have here, whilst with just the blue scattered out, it'll look more like this blue color, but perhaps paler. So close to sunset, green light is also scattered out, so the light coming directly from the sun will look orange or red. Clouds illuminated by direct sunlight may then look red, but the atmosphere will look cyan, a mixture of blue and green. We should not have an atmosphere that looks pink. An atmosphere that looks pink would mean that there's pink light coming into the atmosphere and being scattered by the atmosphere. That means the blue and the red are both being scattered by the atmosphere, and this in itself shows that the atmosphere has to be quite opaque in order for red light to be scattered as well. Now, the atmosphere cannot scatter blue and green over one straight line patch and not in a patch next to it, which is what we see here. So we would have a blue and green being scattered by this patch of the atmosphere, thus producing a red illumination from sunlight, and we would have only blue being scattered in this patch and thus producing a blue sky in this part of the sky. And this is impossible. We cannot have different patches of the sky doing this that are at about the same distance or right next to each other. This is simply not possible. So the atmosphere cannot scatter blue and green. So either the atmosphere blue and green in one patch and just blue in another. So either the atmosphere is scattering blue and green, leaving all sunlight available to illuminate clouds red, or not. Both at the same time is not possible. This pattern can only be produced by a secondary orange emitting light source. This light source seems to be brighter and is most likely, therefore, much closer to the Earth than the Sun. Now, here we have again divergent light beams that are angled downwards vertically, and they diverge. And this, as we know, indicates that there is a light source which is small and is within the Earth's atmosphere. And this light source is most likely right behind this cloud or even within the cloud. So we have an artificial light source and therefore a device or a sun simulator inside this cloud emitting light and giving rise to these diverging light beams. But we also see beams coming, diverging horizontally. So these light beams seem to diverge as the distance to the observer decreases. And this cannot be due to perspective because these light beams are diverging by about the same amount as the light beams we see coming from this light source and coming down vertically. So this shows that so the light rays diverging horizontally above the cloud are diverging by about the same amount as the vertical light beams, indicating that it is not perspective that is causing these beams to seem to diverge. This means that not all diverging shadow boundaries or light beams seen in the atmosphere are necessarily produced as a result of perspective. So in conclusion, although some divergent light effects observed in the atmosphere can be explained in terms of the perspective ideas contained in the term crepuscular rays, in most cases this term is used to hide the truth of what is actually going on. Diverging beams, especially when angled downwards, are evidence of artificial light sources operating within the atmosphere. Diverging shadow boundaries, even if that divergence can be explained by perspective, still indicate that sources other than the sun are illuminating the atmosphere. These sources seem to be brighter and are thus most likely much closer to Earth than the sun. These seem to emit bright orange and red light and are likely to be stellar cores which the Earth has captured. These objects which seem to have made Earth their host body and from which they are absorbing matter and therefore energy seem to be responsible for the unprecedented tidal events that have occurred along various coastlines on the planet. And you may look at article 227, the previous article entitled Stellar Cores Affecting Earth and Possible Connection to Volcanic Eruptions for more details on that. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.